Hello, welcome back to the next video for our Chapter 5 practice problems. So picking up where we left off, we're looking at number 20, which is we're using a Poisson distribution to find probability of fire ants here given a mound here. So first thing we're looking at is finding the probability of 8 fire ants in a square centimeter of a mound. So when we're looking at a Poisson distribution, once again, you can do this on a calculator or by hand. If you use the calculator, it definitely makes things a little easier. For a Poisson distribution, you're finding the mean, and you're taking it to the x power times our natural logarithm of e to the negative mu all over x factorial. And that is our formula for a Poisson distribution. So we're doing this, we're given a lot of information in the very first part here. We're finding the probability of 8 fire ants, so our x value here is going to be 8. And we're given that the number of fire ants per square centimeter of mound is 6. We know that's the average, so our mu is equal to 6. When we put that in there, we write it all out. This would be 6 to the 8th power times our e to the negative 6 divided by 8 factorial. Once again, you can put this all in the calculator. If you go to the sheet that is posted online for your TIE 384, how to find Poisson's distribution. So if you go second distribution, at the very bottom they have Poisson's distribution, and you can find the values there for you. And when you do all this either by hand or using a calculator, you get a value of 0.103, or there's a 10.3% chance of 8 fire ants being on the mound. Next part here is we're finding the probability of no fire ants. The key value here is no fire ants, so our x value here is going to be 0. Anytime we see no or none, those are 0 values. So we would do the same thing. We have 6 to the 0 power times e to the negative 6 over 0 factorial. And remember, 0 factorial is a value of 1. When we put all this in the calculator and we move it out, we see it's 0.00248. You can put that in scientific notation if you want, or just leave it like that. Either way is fine. The next one is the one where the words are probably the most critical part of the problem. So we're finding the probability that at most 4 fire ants are in a square centimeter of a mound. And when we're looking at that at most 4, so we're looking at values from 4 and less, because 4 is at most 4. So we're looking, but 3 is less than 4, and 2 is less than 4, and 1 is less than 4, and 0 less than 4. So at the maximum value is 4, but anything less than that is also in consideration. So it's 4 or less is our probability. So we're trying to find the values of x at 0, x at 1, x at 2, x at 3, and x at 4. And so we have to do a Poisson distribution for each one of these. Well, great thing is we already did 0. We know the value of 0 because we did it above. And that equals 0.00248. You have to do the same thing for 1, 2, 3, and 4, or use a cumulative Poisson distribution on the calculator, and you can find that out as well. So you're following the same steps. Once you get them all, you add them together. So 1 is going to equal 0.01487. 2 is going to equal 0.04462. 3, 0.08924, and 4 is going to equal 0.13385. When we add these all together, the probability of at most 4 fire ants being here is going to equal 0.28506, or there's a 28.5% chance of this happening. Number 23, back to a little bit more of our binomial distributions here. Key part here is we're probably finding probability of only at 4 mothers given, so our x value is just at 4, so x equals 4. We have 19 total mothers. How many different ways can you choose 4 out of that 19? 0.095, or our probability of these mothers smoking, right? Our maternal habits of smoking during pregnancy, to the 4th power, our x value, times probability of q, 0.905, to the n minus x power is 15. Write all this out. Should get a value of 0.0702, or 7% chance of finding only 4 mothers. Next part is, what is the probability between 3 and 6? So remember, these are kind of like your bookshelves. We don't care about the value there. We want to know about the books. So that's 4 and 5 that we're adding together. Well, beautiful thing is we did 4 in the very first problem. So now we're just doing the value of x equaling 5, because we already did 4. And we're just going to add it together. So this is going to be 19, choose 5, 0.095 to the 5th power, then times 0.905 to the 14th power. When we do that, we should get 0.0221. Now we're going to add these values together, so 0.0702 plus 0.0221, and that equals 0.0923, or the probability. That doesn't look very good. Let's try writing that again. 0.0923, or there's a 9.23% chance to find a probability between 3 and 6 mothers, which is the probability of 4 and 5 added together. Last part here is, what is the expected number? So remember, that's n times p, so 19 times our probability of 0.095. Remember, if anything's given to percent, make sure we put it in the correct decimal form. That's going to be probably the biggest issue. Don't try to do some of this stuff in your head unless you feel very confident. Take your time and make sure you have the right values. Because if you have the wrong values, you could do all the work right, but if you have one wrong value, or you don't put a decimal or a 0 in the right spot, you're not going to get the right answer. So what's the expected number? 1.805. Moving on, we have a new problem here, a little stretched out. Hopefully it's better on your page than it is on this particular version. But we're trying to find what is the probability of at least one mother that is currently breastfeeding. So if we're trying to find what is the probability of at least one mother, well, if you have one mother, that's at least one mother. If you have 2 mothers, that's at least one mother too. So is 3, 4, 5, and 18 is at least one mother as well. So we're trying to find the probability between 1 and 18. So we could do a binomial distribution for x equals 1, x equals 2, x equals 3, all the way to x equals 18, and add them all together, and we'd find the probability of at least one mother currently breastfeeding. And that's what we are. Anytime we have a value here, try to replace mother, disease, whatever our population is, maybe with candy. And suppose you have this candy in hands and you're trying to find or take at least so many or up to so many. So that way maybe you can visualize what the problem's asking. So at least one mother is one or more mother all the way to the very end. So we can do all of those problems, x equaling 1 through all the way x equaling 18, and add them all up. That's one way. Or we can use some of the rules that we know about probability, where we know the total sum of the probability is going to equal to 1. So the total sum is going to equal to 1. And if we know what the probability of x equals 0 is, we can then say 1 minus that probability gives us 1 through 18. So if we do 18, choose 0 to the 0.070 power at 0 times 0.93 is our q to the 18th power. And you write this out, you get 0.2708, or there's a 27.08% chance of finding no mothers that are currently breastfeeding. But we want to know the probability of at least 1. So regardless if we get 3 or 7, it's, as long as it's greater, 1 or greater, we'll have satisfied at least one mother. So now we're going to find the complement of this event, which is the probability of this event not happening, the probability of 0 mothers happening, which would be 1 or more. Take 1 minus 0.2708, and we get 0.7292, or there's a 72.92% chance of finding at least one mother. Next problem here is between 2 and 6 mothers. So remember, we don't really care about the bookends of it. We just want to know the books. So we're looking for 3, 4, and 5. And we're going to add all these up. So you're going to find the probability of x equaling 3, x equaling 4, x equaling 5. And you're going to write all these values out as a binomial distribution and add them all together to the 15th power, and that's going to equal 0.0942. When you do 4, it'll be 0.0266, and at 5, it's 0.0056. When you add all these values up together, you're going to get a grand sum of 0.1264, or 12.64%, which is the probability of 3, 4, and 5, or the probability between 2 and 6 mothers that are currently breastfeeding. I'm going to kind of just write this out as quick as I can for that one so you can see all the work. So 18 choose 5 times the probability of 7 to the 5th power times 0.93 to the 13th. So remember, your x values should always be the same value, and if you added your exponents together, it should always sum to the number, or n, that is in your sample that you're looking at. Last part here, number 25. So we're trying to find what is the probability of finding at least 2 females with HPV in the sample. So remember, at least 2. So 2 is at least 2, 3 is at least 2, 4 is at least 2, so all the way up to the very end. We have an n value equaling 6. So you could do what is the probability of 2 plus 3 plus 4 plus 5 plus 6, all those x values, add them together. Or you can do, the total probability should be 1. So if you find the complement of at least 2, which is the probability of x equaling 0 and x equaling 1, add those together and take the complement of that event, you'll find probability of 2 through 6. And that is the way I would do it, because it's less work, or it's less equations to deal with. 0.6 to the 6th power equals 0.0466. And then if you get 6, choose 1, my mistake. 4 to the first, 0.4 to the 1st power times 0.6 to the 5th power equally 0.1864. Add those together and you get 0.233. And we take 1 minus 0.233 equals 0.767, or there's a 76.7% chance of finding at least 2 females with HPV in the sample. Expected number, remember, just a fancy way of saying what's the mean. Our mean is equal to n times p, which is equal to 6 times 0.4, which equals 2.4. And our variance, so remember variance, sigma squared is equal to n times p times q, which is equal to 6 times 0.4 times 0.6 equals 1.44. And there those units are squared. That will conclude this last video. Once again, if you have any questions, let me know. Come see me, email me. Refer to the other information that's on Canvas, and always look at your calculator. Some of these values might be slightly off depending on if you do one huge function or calculator, or if you're using an actual a distribution function for binomial distributions. So these values could be a little off, but they should be right around the same area. I mean, if you're getting values that are more than 0.01 off from each other, there's probably something really wrong. If they're 0.0001 off, that's not going to be that much of a difference in the grand scheme of things. If on this answer you got 14% instead of 12, you could definitely see that that's going to be a problem. That's too much of a variation. But if you got something like 0.1259, that is completely okay. It could just be rounding, or how the calculator is, or how you have it set up. But once again, as long as your work always supports your answer and I can follow along with it, you'll be on the right track. That will conclude this video. Have a great day.